Harishwini.
Matrix number is U2003872.
Hi, I'm Charlington with matric number U2004031.
Hi, my name is Jillian Wong Wen-Yi and my matrix number is S2031481.
Hi, my name is Wang Xinhui with matric number U2003992.
Now, the skateboard. The skateboard is something cool and fun. But how we can relate it to the dynamics? Let's take a look. Hence, in this video, we will introduce the introduction and the real-life example, which is chosen, the skateboard. We will discuss the 3 learning outcomes, which is LO1 to solve the dynamic problems of accelerating particles, the LO2 to solve problems of accelerating rigid body in 2 dimensions, LO3 to analyze kinematics and kinetic problem in vibrating particles, and finally we will conclude with the findings and conclusion. Now before that, how is dynamics related to skateboard? Hence in this video, I will explain the concepts of dynamics on the skateboard, how dynamics of the control motion of a skateboard over a rough horizontal plane could be considered. Next, we will also discuss and explain about the coefficient of the friction on different types of surface which is obtained and compared later. Thirdly, we will relate to the change of displacement and turning of the human's body. Next, we can also relate and discuss about the propulsion force that provides the acceleration on the skateboard. Finally, we will conclude and discuss on the dependency of the skateboard velocity and its trajectory on the motion of the human's body. Now, let's take a look.
Hi everyone, my name is Charlington and now I'm going to explain about the LO1, which is solve dynamic problems of accelerating particles. We are going to find the stopping distance of skateboard on 3 types of surfaces. First, for the 3 surfaces, the mass of the skateboard and the skateboarder are measured. For the skateboard, the mass obtained is 5 kg, while the mass of the skateboarder is 60 kg. So the total mass of the skateboard and the skateboarder measured is 65 kg. Then we can calculate for the weight. By knowing the weight, we can calculate the normal force, which is 637.65 Newton. After knowing the normal, we can calculate the friction force by assuming μ k tau is equals to 0.6. Then we can calculate the acceleration by inserting the values into the equation. After getting the deceleration of negative 5.886, then we can assume that the initial velocity to be 2 and the final velocity to be 0. Now, we can assume that the deceleration is constant and thus we can obtain the distance for the skateboard to stop. Distance for the skateboard to stop at tau surface is 0.68 meter. Next, for the cement surface, the steps are repeated like the previous example until we get the normal force. So, after knowing the normal force, we can calculate the friction by assuming μ k cement is equals to 0.8. Then, we can calculate the acceleration by inserting the values into the equation. After getting the deceleration of negative 7.848, then we assume that the initial velocity u to be 2 and the final velocity to be 0. Now, we assume that the deceleration is constant and thus we can obtain the distance for the skateboard to stop. Finally, we obtain the distance for the skateboard to stop at cement surface is 0.51 meter. Lastly, for road surface, the steps are still the same like the previous example until we get the normal force. So after knowing the normal, we can calculate the friction by assuming μ k root is equals to 0.9. Then we can calculate the acceleration by inserting the values into the equation. After getting the deceleration of negative 8.829, then we assume that the initial velocity to be 2 and the final velocity to be 0. Now, we assume that the deceleration is constant and therefore we can obtain the distance for the skateboard to stop. Distance for the skateboard to stop at road surface is 0.45 meter. Next, this is the tabulated data for coefficient of kinetic friction, acceleration, and distance for the skateboard to stop for 3 types of surfaces. So let us analyze the data in this table. From the results we obtained as shown in this table, we can make a conclusion that the rougher the surface, the greater the coefficient of kinetic friction. So the friction acting on the skateboard will be greater, and the higher the value of deceleration. And therefore, the shorter the stopping distance for the skateboard. Thank you.
LO2. Solve problems of accelerating rigid bodies in 2D. A scenario is created where there is a skateboard A is running to another skateboard B. Ouch, that would be a painful scenario. Let's assume that the total mass of the first skateboard and its skateboarder MA as 65 kg, while the other one MB as 50 kg. Also, we assume that the initial velocity of A, VA, is 2 meters per second, while the initial velocity of B, VB, is 3 meters per second in opposite direction. As we know, the total initial momentum will equal to the total final momentum as the momentum of a system is conserved. Therefore, we can obtain the result VA equals to negative 2.5 VB, where an elastic collision will occur between A and B. In this scenario, A will move in an opposite direction of B with a velocity of 2.5 times of B. Next, for the conservation of energy, we created another scenario where the skateboarder is skating in a half pipe, which is a cool trick but not for beginners like me. Initially, the skateboarder is standing at the top of the half pipe. Then the skateboarder will skate down the half pipe. We assume that the half pipe has a height of 2 meters. We now need to find out the total energy possessed in the skateboarder when he is at his initial position, which is the highest point of the half pipe with the height of 2 meters and with his initial velocity V1 equals to 0 meters per second. Next, we have to find out the final velocity of the skateboarder V2 when he is at the lowest point of the half pipe, where the height is equal to 0 meters. Based on the conservation of energy, the total initial energy of a closed system will equal to the total final energy. There are two types of energy to be considered in the calculation, which are gravitational and potential energy and kinetic energy. By inserting the values into the equation, we can calculate the final velocity of the skateboarder at the lowest point of the half pipe, which is 8.86 meters per second.
Now let us move on to LO3, which is to analyze the kinematics and kinetics problems in vibrating particles. So what is vibration? Vibration is the oscillating motion of a body or system of connected bodies displaced from a position of equilibrium. For part 3, another scenario is created where a skateboarder is skating with a velocity of 2 meters per second on an uneven surface. This is a forced vibration problem instead of free vibration, as it consists of friction and external forces. First, the original height of the board is measured. Then, the y displacement of the board is calculated after obtaining the final height when the skateboarder stands on the skateboard. We obtain the y displacement of the board as 0.5 cm. Then we can calculate the spring constant of the skateboard bushing, assuming that the positive y displacement is downwards. Here we get 255,016 Newton per meter, which shows that the skateboard bushing is very hard, or we can call it stiff, where it is very hard to be stretched or compressed. Next, we calculate the natural frequency of the bushing by using the spring constant we found. The natural frequency found here is 62.6 radian per second. Then the angular velocity of the wheels is calculated where we got 80 radian per second. After obtaining the angular velocity, the force caused by the unbalanced skateboard wheel is also calculated. We obtain 192 newtons for the centripetal force. Lastly, by using all the information we found, we can find out the amplitude of the steady-state vibration, which is 1.19 mm. This means that the vibration is quite small in this skateboard.
Now, let's recap and conclude. What did we find? We found out the concept of dynamics on a moving skateboard is analyzed and calculated using the equations of motion. We found out that the motion of a particle is governed by the Newton's second law relating the unbalanced force of a particle to its acceleration. Next, we found out that the friction force of each different surface could be compared, and the rougher the surface is, the greater the friction acting on the skateboard. Thus, the shorter the stopping distance for the skateboard. Next, we also found out that the conservation of momentum and energy of the skateboard are proven when there is collision between skateboard A and skateboard B. We also found out that the elastic collision are shown as the objects are separated after the impact has taken and they did not lose any of their kinetic energy. What else did we learn? We learned that potential energy is stored at greater heights. When a skater is at the top of the ramp, we notice that the skater has a higher amount of potential energy. We also found out that the kinetic energy only occurs when a person, an object, is in motion. The faster the skater moves, the more kinetic energy the skater has. Finally, we have learned that the conservation of energy states that the total amount of energy involved in the transformation must remain constant throughout the system. Hence, what we can conclude throughout the video. We can conclude that we are able to achieve all three learning outcomes, which includes to solve the dynamics problem of accelerating particles, to solve the problems of accelerating particles of rigid body in 2 dimensions, and finally we are able to analyze kinematics and kinetic problem in the vibrating particles. Finally, that's all from us. Thank you.